last time, and the idea is that we are going to do three things. So the first thing that we are going to do is a little bit about, let's say, more on, let's say, circuits in general. And here, the idea is that I'm going to tell you about three ingredients that happens everywhere. So one is the so-called n-fold Hadamard. The other is classical computing with the Toffoli. And the third one is essentially, let's call this 1, this 2, and essentially doing 1 plus 2. And this will give us quantum parallelism. So this is the first part. Then we will talk a little bit about the query model, which in a sense is going to give us a high level from, and I'm using the terminology of let's say, programming, so a high level and low level, let's say, so will give us a high level view on how to build algorithms without going into the subtle detail, but we will use the query model for that. And then finally, we will describe the very first two algorithms. I mean, we already did quantum teleportation, but let's say two algorithms that historically, in a sense, gave a bump to the quantum computing business. And one of them, I'm a disaster with names, so I will use just the initial D and J algorithm, Deutsch and Jost. Okay, I'm a disaster with names. Anyway, DJ algorithm. And the second one is the so-called Bernstein-Vasirani algorithm, which are essentially almost the same thing, but not really. So this is the plan for today. So let's start with this. So the n-fold Hadamard, so n-fold H. So this is really, let's say, a very, very used, let's say, subroutine that essentially enters in almost all the quantum algorithms that you can think. And the idea is that suppose that you have n qubit, and you consider this simple circuit. You take H tensor n acting on 0 n. So 0 n means 0, 0, 0, 0 n times. So visualizing, if you want, the circuit is this. You have 0, 0, da, 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 0. Then you have many lines. And here you put, for each of them, you put an H. And then it goes. And we want to, I mean, here, so we will have a state, psi, and we want to understand what is the state. This is really typically the starting point of the vast majority of algorithms that you will ever see. So let's see. So the idea is that we want to see who is this beast. Okay, so this is super simple, right? I mean, we already know that H acting on 0 just creates the state plus. So this is simply the state plus, tensor, da, 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 tensor, plus n times. So per se, doesn't look really something exciting, right? I mean, it's just a product state, no entanglement. Not surprisingly, because we didn't put any 2-qubit gates. But however, it's very important. And how to see that? Well, what we have to do is to expand each of these beasts. And we know that this guy becomes 1 over square root of 2, 0 plus 1, and so on and so forth. So then we take all the possible tensor products, right? And at the very end, we end up with psi equal to 1 over square root of 2 to the power of n, right? And then we get summation over all the j's belonging to the set 0, 1, n of j. Now, do you know what I mean with this? Should I specify a little bit better? Yes, good. So I should specify that this, I'm saying, take all the possible n strings made by 0 and 1 and sum all together. So in practice, this state becomes the state 1 over square root of 2 to the power of n. Okay, become, sorry, times 0, 0, 0, n times plus 0, 0, 0, 1 plus da 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 until 1, 1, 1, 1, everything 1. So how many states do I get in total? 2 to the n, exactly. And how, so that means that this circuit creates a uniform, because they have all the same factor in front, creates a uniform superposition of all the possible classical states. So this is, let's say, a very used subroutine all the time that, not all the time, I mean, often when we start an algorithm, we use this, because it's a very convenient way to, in a sense, initialize our register of qubits in a, let's say, superposition that includes all the possible classical states. And then we will do more, let's say, funny things. Okay? Now, the next, let's say, small thing that we are going to say is the following. What happens if I do exactly the same? And keep in mind this formula because it will become useful later. What happens if I do exactly the same, but on a given state I, where I is a product state? So I could be, for example, 0, 1, 0, 0, 1, 0, 0, and so on. What happens? Okay, good. So we will get something that goes like, in this case, plus, minus, plus, plus, minus, plus, plus, which means that essentially this guy is going to bring some minus sign, right, some phase on the one input. Cioè, this guy is going to be 0, minus 1, with the usual square root of 2 here, instead of 0 plus 1. So in a more, let's say, compact way, exercise, let's say, check, that this can be written as 1 over square root of 2 to the power of n. By the way, in the lecture, I put everywhere the n in the wrong position, right? Because I put it here. So in the lecture notes that some of you probably already have, it's always here that is probably wrong, I will say, right? N should be should stay here, right? Should stay on top. No, I'm an idiot. I'm an idiot, sorry. Yeah, sorry. Okay? And then summation over j of between, let's say, 0 and 1 to the n. And then we get minus 1 I scalar product j, where I, this guy, read summation over all indices here, let me call them k, ik, jk. So we get essentially almost the same state as before, but we have a remnant of the initial state I, which is going in the relative phases between the various components. So this is a way, if you want, to encode a memory of the original state I that get encoded into the relative phases appearing here and there. Notice once again, I mean, let me stress the obvious, that once again, if we were working with probabilities, this and this will be exactly the same because we don't have the freedom to put some minus sign with probabilities. So once again, we see that the extra freedom that we get by quantumness is, in a sense, the presence of the various minus signs here and there. Questions? No? Yeah, please. Yes. What is your question? What I mean by this? I mean, the minus is coming because yeah, if you want, it's like, okay, it's like you retake exactly this, but now your I is not 0, 0, 0, it's 0, 1, so it will be like here, you don't have this, you have this. So this, when you arrive here, create a minus state. And when then you, let's say, unfold the various products, you end up again with all the possible classical strings, if you want, all the possible classical states. But here and there, you will get some minus sign determined by the scalar product between I and J. Fine? Yeah. Please. Is this. You sum for k going from 1 to n, I, the string, you know, both I and j are strings of 0 and 1s. And so you take, for example, so let's say that this is I and this is j, right? And let's say that this is, let's say, 1, 0, 1, and here you have 1. So you get 1 plus 0 plus, sorry, 0 plus 0 plus 1, and so you get a 1. Okay, so far so good. Now, so this was point 1. Point 2, so classical computing with Toffoli. So the idea is the following. What we are gonna now say is a little bit obvious, but still. Can we do classical computing with a quantum machine? The answer is yes, and let's see how. Of course, again, this goes in the direction of what we were saying before. Let's say if you just use a quantum computer to do something that you can do classically, is a very bad idea, but we will see that there is much more than that. So suppose that we have a classical Boolean function, which is an f of x that goes from, let's say, from 0, 1 to the power of n to, I mean, we could be more general, but let's be simple. That goes to 0, 1. So this is a function that eats strings with n bits and spit either 0 or 1. Could be more general and put an m here, but so spits another string with another dimension, but let's confine for the moment. So this is what classical computing is, right? Essentially, electronic, if you want, is building functions like this with some circuit. Now, there is a theorem that we are not going to prove, that any f of x, let's say, can be reconstructed. No, sorry, can be built, let's say, by and sorry, vabbè, you understand there are two different ands, and not classical gates. So if you can, let's say, construct the NOT gate, the classical one, and the AND gate, the classical one, you can do whatever you want. I'm not, I have no idea about the proof, but it is true. Now, so let's say we have to, so now our purpose is to show that we can build the NOT gate, the classical one, and the AND gate with some quantum gate. Now, the NOT gate is essentially trivial, right? We have already the NOT gate. We have the X. So now our purpose is to build the AND gate. And you remember, the AND gate, it's a gate that requires, let's say, now let's avoid the cat notation because we are talking about classical things, right? So something like that. And here we get, let's say, here we have A, and here we have B, and here we have A and B. And we know that, let's say, 0, 0 gives 0, 0, 1 gives 1, 1, 0, 0, 0, 1, 1 gives 1, right? This is the AND gate. First of all, you should immediately complain about the possibility to make this quantum. Somebody knows why? Exactly. This is absolutely irreversible. We have 2 bits that enters and 1 bit that exits. So for sure, our quantum implementation should be slightly different. So we want, let's say, something that is reversible, but that still obey such a rule, let's say. Any candidate? Okay, somebody vote C-Not, somebody vote Toffoli. Who vote Toffoli? Just one. Who vote C-Not? 0. Who doesn't vote? Who prefer to avoid to vote? Everybody. Okay, good. Yeah, good. So, yeah, she's smart. She noticed that I wrote there Toffoli, so she immediately said, okay, it must be Toffoli. Correct. Let's see why. Yeah, this is a bit cheating, I have to admit. But okay, so let's see how it works. Well, the idea is that, well, it's simple, I do it. So the idea is that you encode your A bit in a cat, you encode your B bit in a B cat, and then you put here a free qubit that you initialize at 0. And then you go with a Toffoli. And it should be quite easy to see that if just one of the two between A and B is 0, nothing will happen to this guy, and so we will get 0. If one of the two, if both are 1, this guy will become 1. So this is a way to implement the AND gate. So essentially, what this simple, let's say, thing is telling us is that by using circuits of Toffoli gates, in principle, it's possible to do any Boolean function that we wish to do. So any classical Boolean function can be reproduced only, I'm saying only, yeah, okay. Why I said, somebody knows why I said only by Toffoli? Cioè, in principle, I said this use the X gate, right? Is there a way to implement the NOT gate using the Toffoli? Let's hear her here first. You give up, essentially, right? Yes. Okay, the other one? Yeah. Very good. So if you set A and B to 1, you get 1, 1. They enters into the Toffoli, and let's say they activate the Toffoli, such that you get A, and A, they get always negated, right? So, I mean, it's a triviality. Once these two are 1, essentially this guy is always acting as a real NOT. So this is just to say that, okay, so Toffoli can do whatever, yeah, here, of course, this is going out. So Toffoli can do all the classical things. that's it. So this is what I wanted to say. And so now we are ready for the next, let's say, ingredient, that is quantum parallelism. Okay, so here is the following. Suppose that we have a circuit that do the following thing. So we have two, let's say, registers. So we have a set of qubits that I call I, that can live in 0, 1, right, to the power of n. So I have n qubits that can take any possible, let's say, classical value. And here I put an extra register, so an extra qubit, that I initialize to 0. And suppose that I have then, it's not as, I mean, we showed that this is possible. We have an extra, we have a circuit that I call U, that give me, let's say, I still in this configuration, F of I. So this is not black magic right now, because we know that the Toffoli gates allow us to reproduce any Boolean function. So this U might be complicated. I'm not, let's say, saying that it's simple, but there must be a circuit that can reproduce a given Boolean function that we want to implement. So this is, if you want, a way to, let's say, implement the result of a Boolean function starting from an input that is coming in the first register and then goes in the last register, we get the result. Good. Now, yeah, please. I don't deny. Quantum parallelism. Yes. Yeah. Okay. Yeah, please. It's just a sequence of bits, yes. So let's say that you start from a classical state, initialize in some classical product state, let's say, and you have a circuit that when you have this guy, spit out in the next register, spit out the value of f of I, and f of I is given. And you have a circuit that implements that. So roughly speaking, the idea is that you have your n guys, n. They enter in a black box that do something, in a sense, unknown to us. There is an extra guy that is arriving here that is initialized at 0. And as a result, you receive back all the n guys untouched. And here, you receive f of I. And as I said, this can be done using only Toffoli. F of I can be 0 or 1. So Pauli, no, right? Pauli is an operator. So you mentioned it Pauli, but you wanted to say something different, right? Pauli is an operator, here is a state. No, because this is a. We will see in a moment. We will see in a moment. But if if you want you are implementing something like this, right? So if you receive a classical state, the result is yet another classical state. Okay. Good. So this is our initial circuit, right? Now, what happened? If we take our n qubits, we put an Hadamard on all of them, then here we still have our spectator that is 0. Then we receive our black box, U, and we end up with if you want, the same here. But here, what we get? Let's do the computation. So after this, we get, so what we have to compute using this, right? We get U acting on 1 over square root of 2n, summation over all the possible I belonging to 0, 1 to the power of n, I 0, we didn't do anything over that, right? Now we act, and so we get 1 over square root of 2n I belonging to 0, 1 to the n, I, did I do a mistake? Ah, okay. I, f of I. And now we see the black magic. We just run the circuit once, and in particular, we use this unitary operation only once, and as a bonus, we got all the possible outcomes of the Boolean function. So suppose that you want to do this classically, you should evaluate these circuits 2 to the power of n, I arrive, 2 to the power of n times. This is, in a sense, a first manifestation of the black magic. You use quantum superposition to recreate all the possible outcomes of f of I with a single, in a language that we will use in a moment, with a single query. So we just use the circuit once, and you have all of them. Yes. The Hadamard, exactly. So you pass from 0, 0, 0 to all the possible 1, then you enter with this huge superposition into the circuit, and in a single operation, you get everything. Yeah, this is something we said last time, you remember. At the beginning, we always assume to start from a reference state that is 0, 0, 0. Hopefully, if I don't forget, I will always assume that we are in 0, 0, 0 before doing anything. Otherwise, I will specify. Yeah. Now, should we be excited about this, or at the very end? Yeah, let's see. What do you mean compensated? Okay, good point. No, it's not compensated for the following reason. This U is probably an horrible beast that include all the possible. Suppose that you come with a Boolean function that is extremely cumbersome and require an enormous amount of let's say of computation and so on. The Hadamard are much cheaper. So yeah, let's say that you pay a little bit of price putting the Hadamard, but at the end you gain dramatically, because instead of running this circuit 2 to the power of n times, you run it only once at the price of adding n gates. So overall, you get a huge advantage. Now, should we be excited about that? A little bit, we should, but should we also be careful? Typically, when I ask a question in this way, it means that you have to be careful, but somebody knows why? Okay, we have a candidate. Very good, very good. The point is that we have this beautiful state that introduce all the possible f of z, right? F of I, sorry. But it's still a state. If we want to make any use of this guy, there will be a moment in which we will have to measure this guy. And we know that by measuring, this will collapse to just one particular case of I bar, f of I bar. So in a sense, if we don't do anything, and I bar can be whatever. So, and notice the probability is the same for everybody. So if we don't do anything more than that, this is just a randomized classical algorithm, no more than that. So we could be able to replace all this machinery with a coin and a classical circuit. Well, many coins, but okay. Toss these coins, decide what is I bar, and then run the classical circuit. So far, nobody will be satisfied by this classical application. So what quantum magic should have to do for us is to provide something more than this. Comments? Okay, so this ends part one. Now we go to the query model that is almost a summary of what we did so far with a small twist. So the query model, as I was saying, is a little bit like, let's remember, I mean, in the first lecture, we said that one of the keyword, or let's say one of the key tasks that people in this business do every day is to talk about complexity. So how many operations, how much time do we need in order to run a certain algorithm, and compare with the classical complexity to see if there is an advantage, how it scales, and so on. Now, where is it? Sorry. Yeah, the query model. So essentially, the query model, it's a model to count complexity in a sort of high-level way. So instead of caring, it's a little bit like your question before. Instead of caring about all this small stuff, we care only on how many applications we do of the big chunk of the algorithm that is taking time. And we will count complexity in terms of how many times we have to run the complicated part. This is, if you want, the logic. Now, to be a little bit, let's say, more practical, this is done in a more abstract way, but is essentially the same thing. So the setup for the query model is the following. So we have an n 2 to the n bit register, classical, right? So this is, we call x, and I call x equal to x0, x1, xn minus 1, and I have that each xi belong to 0 and 1. And this I call it memory, or I call it, somebody call it oracle, because, well, okay, let's avoid history. Somebody call it oracle. And this is a sort of information, is a little bit like a RAM memory in a computer. It's a sort of information that is, in a sense, stored somewhere and that I can access. By the way, this is nothing but this, right, for all the possible outcomes. I could, let's say, imagine that this is just a convenient way to say that each xi is one outcome of this guy. And the numbers match, right? Because we have small n qubit that can parameterize 2 to the n classical states, which is this guy. So this is nothing but the application of a function in this quiz. So we have our oracle that stay there. And then we have, so if you want, we could say that this is simply a set with f of 0, f of n minus 1, with all the possible outcome of a certain Boolean function that I apply. And then we have a memory access. So, yeah, please. No, no. Yeah. And then I have a memory access, which means that I have an operation that I call OX, to remember that, let's say, the memory name is X, that take I belonging to 0, 1 to the power of n, 0, and spit me out, again, my I and the corresponding xi. Whenever I do an application of this kind, I do what I could call a query. So the idea is that I'm essentially running the U operator over there, and I'm writing the result of the U operator in the next register. It's exactly the same thing, a little bit more abstract. I don't specify what is the function that I'm computing. I'm assuming that I have a memory with all the possible outcomes, and I'm just accessing them by query. Okay? Now, of course, this is not a well-defined operation. Why? I have to say what happens on 1, right? To make it linear, I need to say. So I complete this declaration by saying that OX over IB split I B plus xi. And this is what people call the so-called standard query. Okay? So every time I need to access the memory, I need to do one operation of this kind. Now, so from now on, we will most of the time talk about query complexity. So we will ask how many, to run a certain algorithms, how many access I have to do to my memory. So query complexity will be simply a count of how many times I call the oracle. Right? Assuming that this is by far the most expensive part of the algorithm. So coming back, we will always forget about small gates, Hadamard, and so on, and we will concentrate our complexity on computing this. So in particular, people also talk about time complexity, which is a more sophisticated, not really more, if you want, more low-level version in which you consider also the other part of the circuit that here we skip. In this sense, I call it a more high level. Now, let me, before going to actual algorithms, let me also introduce another way to essentially do the same operation that sometimes can be more convenient, which is the so-called phase query. This is essentially an exercise. So suppose that we implement a standard query, but we decide to put B instead of 0 and 1, we decide to do OX over I minus. What happened? Well, simply, we get OX acting on I tensor 0 minus 1 square root of 2. Now we act with OX, so this becomes 1 over square root of 2 I xi, right? Minus I 1 minus xi. Am I saying correctly? I think so, right? Well, 1 plus, but okay, nothing changed. It's the same. So by now putting things together, I think all of you should convince, and if you're not, do it as an exercise, the details. This becomes exactly the same of minus 1 to the xi, I minus. So we see that our extra qubit start and end in minus. So from this point of view, nothing changed. And the result of the query is now on the phase. So this, and then people, let's say, used to call this OX plus minus, that acting on I gives minus 1 to the xi, I. But pay attention, this, technically speaking, is an abuse of notation in the sense that this query is actually acting on I minus. It's just that minus starts in minus, ends in minus. You can, let's say, forget about it. But it's an abuse of notation. The real, in a sense, machinery is this one. Can you, good, exercise. What is OX, let's say, what is OX acting on I plus? Somebody knows already the result? No, yeah, okay. This, you are telling me how to compute, and it's a good answer. If you do the computation, it's a very simple exercise, you will see that this becomes I plus. So actually, this is a way to don't do the query. If you, no, it's not. You have, if you want, you have a freedom to decide over which qubit you want to act with a given query and which qubit you don't want to act. If you initialize the ancilla qubit in the state minus, you get a phase. You might get or not, depending on xi, of course. If xi is 0, you get nothing. But, or you can simply avoid the query going in this way. Okay. Now, in the last 15 minutes or so, we can go to, so if you want, this concludes the technology, if you want. Now, we finished all the technology, all the prerequisite. And yeah, as I said, the setup of the problem that we are going to study now is to consider some problem to solve. Problem. We will give a quantum solution, counting the number of queries. We will give a classical solution, counting the number of queries, and we will see who wins. And hopefully, we will find example in which the quantum part is winning well. Questions? Please. Not really, right? This is just a simple way of thinking. You could say that this is actually our U circuit that implements the function f here. Because each xi can be the result of f of x with a different I, if you want. So this is just, let's say, practical to think. But what you should think about that is really like a black box, a unitary operation, heavy, and this is why we count complexity with that, because it's the heavy part, that perform the computation. Okay. Yeah, please. Can you repeat? Uh-huh. Well, no, okay, good point. When we do comparison, we assume that the same oracle can be accessed by a classical algorithm and a quantum algorithm. this is part of the research, if you want. You might, if you want, what typically happens in this field, as far as I know, is that people come out with a certain oracle and a certain circuit that have a certain complexity, and they say, okay, this is an upper bound on the possible complexity to solve this problem, and then somebody come out and say, oh, I found a better implementation that reduces the number of queries, and then there are people that can even do more and say the best possible complexity goes in this way. And there are very few algorithms that achieve that. But this is part of your research, if you want. If you find a better oracle and a better algorithm, you have a new research paper. Okay. So, other? Okay. So now we go to the first algorithm. So we start to play something, let's say, more interesting, probably. And the first algorithm that we are going to solve, as I said, is called JD. As far as I understand, was the very first algorithm that gave, let's say, a hype or, let's say, a huge interest in quantum computing. So historically, it's very important, and also, let's say, practically. Yes, it's called sorry. Joshua, credo, I think. Okay, so let's see the problem. We have an n-bit string x equal to x0, xn minus 1, that you might think you have a circuit that implement this function with this output, okay, with n equal to 2 over n. Sorry, this doesn't make sense. Like this, okay? And we know that this guy can arrive in two versions. So we don't know which of the two, but we know that there are two possibilities. A, all, let's say, all xi are equal. So all 0 or all 1. Or B, exactly n over 2 equal to 0 and n over 2 equal to 1. We don't know which of the two, and we want to discriminate between these two possibilities. Now, let's start classically. So suppose classically, what can we do? We can just, let's say, start to call and check x0, okay. So suppose that, so classically, and suppose that we want to be deterministic. So we don't admit possibility of mistake. Suppose that, let's say, your life depends on this answer and you absolutely don't admit any possibility to make a mistake. How many queries do you have to do in the worst case in order to be sure that you do the proper answer? No, you are very pessimistic. Correct. And n half plus 1. Because if, suppose that I'm, in this case, A, even if I see n half zeros, in principle, I cannot be sure that I'm not in this case. I could be so unlucky that I extracted all the zeros and all the rest will be 1. So if I want to be deterministic, my complexity goes like n divided by 2 plus 1. Yes, absolutely, absolutely. Either A or B. This is the promise that somebody gave you. And you want to discriminate between these two. So this is, now suppose that, okay, your life is not so threatened by this result, so you admit a certain probability. So you want to be probabilistic. So what is a possible, so suppose that you assume a certain threshold P, so you want to be sure that you answer correctly and the mistake is smaller than a certain probability P that I don't want to specify. How many queries do we have to do? Okay, let me put the question in a bit better way. The number of queries that I have to do is dependent on n or not? No. The reason is because I know that could be that n divided by 2 are 0 or not. So let's say once I extract, for example, 3 guys or 4 guys, and they are all equal, the probability that I'm unlucky, it's independent on that. So the good point is that my O can be of order 1. So I don't need to, I can do a finite number of queries, and the probability is that 1. Because if you want, the probability of extracting, once n is sufficiently large, the probability in the worst case of extracting the wrong, let's say, all zeros is always 1 over 2. Should be, I mean, n divided, and the denominator diminish a little bit because become n minus 1, n minus 2, and so on and so forth. But if n is large, I can ignore these small things, and it's always n over 2 divided by n, right? So it's always 1 over 2. You buy. Okay. So let's say there is a huge discrepancy classically between the two possibilities. If you are, let's say, deterministic, you have to query an enormous amount of time. Yeah, please. No, when I say one query, I don't mean one query, but I mean a number that depends on the P that you decide, but it doesn't, to reach a certain probability threshold, you don't have to worry about n. So if yes, it's, let's say, O f of P, but independent on n. Okay. It's actually not a so difficult exercise to put the two things together. I mean, but let's say, for our purposes, we see this huge separation. Now, let's go quantum. And let's consider the following circuit. So, what? Okay. So, we have our qubits, and we put n, right? And they are all in 0. Then we apply a single OX plus minus. So I apply a single query to the oracle. Then I exit again with my n qubits. And I put another Hadamard everywhere. Sorry. And let's say that, sorry, I forgot. Here there are other H. So I put H everywhere before and H everywhere after. So something, is it clear, the circuit? Yes. Okay, so I put H here, and then arrive here, and I measure the outcome. Let's see what happens. Okay, so here is an exercise. So what happens immediately, let's say here, the state here I write, and I write like psi after the first, let's say, layer of gates here. This guy become 1 over square root of 2n summation I belonging to 0, 1 to the power of n, I. Right? I'm just using one of the formulas that we saw before. Then I arrive here, and I do, what I get is the superposition, right? So what I get here, if you want, when I exit here, I got psi 2, and this is, once again, 1 over square root of 2n, summation over I 0, 1 to the power of n. Yes. Sorry, I'm confused. Yes. Minus 1 to the xi, I, right? I simply put, the oracle for each I gives me this guy. And then I apply again the Hadamard. So I arrive there. And what I get is this apparently a bit cumbersome formula, psi, let's say, 3, which is 1 over 2n, 1 over 2 to the power of n, I belonging to 0, 1 to the n, minus 1 to the xi, and then I do an extra Hadamard, so what I get using again, thanks, minus 1, and then I put an extra Hadamard, 0, 1 to the n, and we learn that this is another minus 1, I, scalar product, j. So this is the result. Not so exciting so far, but now we notice that let's put I equal to 0, 0, 0, 0, and so on. Sorry, no. Let's put j equal to 0, 0, 0, 0, and so on. Now, if I put this, I scalar j is equal to 0. So let's say the final state, psi 3, that of course can be written like a coefficient alpha 0, 0 to the power of n plus stuff, I can easily compute this guy, because for j equal to 0, which is this guy, this becomes a 1, so I have that alpha 0 is simply 1 over 2 to the n summation over I of minus 1 to the xi. And now I notice the miracle. The miracle is that suppose that all the xi, suppose that xi is equal to 0 for each I, this guy becomes simply alpha 0 is equal to 1. Suppose now that xi is equal to 1, all of them, which is one of the other case, if you want, alpha 0 become equal to minus 1, probably, right? Yes. And now suppose that you have half 0 and half 1, alpha 0 becomes 0. So now we see that by simply measuring the state, either we will always get 0 to the power of n, and we will know with probability 1, because the coefficient is 1. So either with probability 1, we will get the state 0, and we will know that all the xi were equal. We don't know if they were all plus 1 or 0, but we know that they were all equal. Or the probability to extract 0 in the case in which the xi were balanced is exactly 0. So if we measure anything else, we know for sure that we were in this case. So, summarizing, the quantum algorithm is deterministic and makes only one query, exactly one. So we get a result which is, if you want, as good as the best probabilistic algorithm, classically, with full deterministic knowledge with a simple query. Is it clear? Okay, can I 2 minutes for the last one? Okay, now we do the other, which we'll use if there are no, okay. So now we do the other algorithm that is essentially the same thing, but with a different, if you want, we will use exactly the same circuit to solve another problem. So the problem is the following. We have again our oracle that is there, but now we have we know that our x going from x0 to xn minus 1, we know that, let's say, it exists a certain a belonging to 0, 1 to the power of n, such that each xi can be written as I scalar a mod 2 for each I belonging to 0, 1 to the power of n. So we know that essentially all our x here are entirely determined by an unknown string of n bits, A, such that this relation is correct. Now, classically here, there is no possibility. Deterministic or not, we have to query all, sorry, because we have to do this, so these are n, small n, so this must be also small n. So there is no way we can be probabilistic or not, but we have to query, so classically, we need to make O(n) queries. Because essentially we have to learn all the possible bits of this string, of these small n bits. We have no way, no other way. So classically, these are always necessary. Now, let's use exactly the same here. And when we arrive at psi 3, right? Let's see, No. Psi 2, right? We have to take this guy and replace. And this guy, by construction, is equal to I scalar product A mod 2. Now, the mod 2 as a factor in the exponent does nothing, so we can forget. So we just remain with this. And now, so we end up that this is 1 over square root of 2n, summation over all the I, minus 1 I scalar A equal, cat I. And now when we re-go with the Hadamard, if you check in your notes, after the Hadamard, so after putting H n over this beast, we get exactly A. So what we have to do is simply to measure the state, and the outcome is telling us exactly A. So in this case, classically, we have to do O(n) query. Quantum, we have to do O 1 queries, and so we get a polynomial advantage in the number of qubits. And there is no, so if you want, this was a little bit, well, okay, it's clear, but this was a little bit, let's say, you could always say, well, come on, I have to build a quantum computer just to gain a little bit of probability. Not really. This, it's really something that is giving a polynomial advantage no matter the error probability that you decide to do. Okay, I think we can stop here. Next time we do other algorithms.
Yes, I don't know if I understand very well. I think that the object of using an oracle is to get like the function that we are.
Exactly. You don't want to. You don't want to, let's say, make your hands dirty with details related how I create a circuit that do this function and so on. You just know by the theorem that we mentioned it at the beginning, plus the properties of the Toffoli gate, that whatever oracle can be implemented. And you say, OK, there is. I know that it will be a pain, so I will count my complexity by the number of times I have to access this oracle.
And often, where does that function comes from? Because I think that it's like a little bit abstract, mentioning a function, but I mean, the function will have like certain values.
Okay.
I think the
yeah.
But I mean, what is the meaning of the function?
It depends. I mean, this function, I mean, is a Boolean function that could, let's say, compute the result of some operation and that you want to access. People in cryptography, as far as I understand, work with this machinery. I mean, here, let's say, we don't care too much about what you are going to use this. We want to see what is the power of this machinery, and if we can, let's say, I mean, you will have, starting from next time and then the 4 lectures, we will really discuss some practical, because these two, let's say, are a bit abstract, I agree, but next time we will start to discuss about the Grover algorithm, that is essentially searching in a big database one element. And this has applications everywhere, right? When your hard disk is crowded, it's always a pain to find the proper files. So yeah, these algorithms are, I mean, probably they have applications. As I specified the first time, I'm not a computer scientist, so I don't know exactly what you can do with them. But definitely searching in a database is something that we do often, right?
Thanks.
Other questions? No? Okay, so let's thank Dario again.
Okay, I have a very small announcement. I realized that what was supposed to be the 4th lecture, which was about quantum random walk, was definitely, let's say, too fast, and I decided to skip. So we will do lecture 3 plus some extra exercise in the next 2 lectures. The 4 lectures is still there. If somebody wants to read it and want to discuss, I'm happy. And that implies that the problem 18, which is still to arrive. I mean, we didn't discuss this. But with what we are going to do, problem 18, the number 2 will be not covered, but number 1 can be done. Okay.
So people now can stay